Hi, welcome back to es346 Basic Thermodynamics. This is module 2.3 Work Interactions. The corresponding sections to the textbook are sections 2.4 and 2.5. So here's the learning outcome for this module. At the end of this module, you'll be able to calculate the amount of work for several different types of processes. Okay, let's go ahead and review the definition of work. We saw this in the previous module. The work is a form of energy, and it can be quantified as the force through a distance. So before we looked at an example, of a block where we were pushing it along the surface. So here I'm going to go ahead and push the block up. So if I go ahead and have a normal force on this block and push it up here, I'm going to do an amount of work. And it's actually going to increase in energy by that potential energy distance there. Now, work is path dependent, which means how I get to that final destination depends on how much work I put into it. So, for example, let's go ahead and push our block up the hill again, but I'm going to draw a different type of surface this time that goes up and then back down and then up to a final distance here. I'm going to go ahead and push the block, and it's going to go up here, and then it's going to go down, and then up there. So now if I look at the amount of change in energy, its potential energy is going to be related to the height that I've gone here. But if I look at the amount of work I put in, I'm going to have pushed it up that hill, and I'm going to have pushed it up that hill. And those two distances are larger than the total change in energy. So therefore, this is known as work being path dependent, in that not only do I need to know its end state, where it ended up here, I need to know the different path that it took. So let's go ahead and work through a few examples. And this first example is going to be very similar to the one we saw before. So in this problem, you can go ahead and maybe pause the video and read it. We have a piston cylinder device. We have an initial condition of 100 kilopascals on a cubic meter. And we're going to go ahead and compress it to 1/2 of its initial volume. And we're told it stays at a constant temperature of 25 degrees Celsius. That's what isothermal means, a constant temperature. And we want to find out how much work is required. So here on the right, I show a piston. We're going to go ahead and exert a force there. Its final state is going to be 1/2 of the volume. And assuming that this piston is tightly fitting, all the material will remain inside the cylinder, which means the pressure will go up. So here we're going to, again, calculate the amount of work. And we know that the work is the integral of a force through a distance. And the force is pressure times area through that distance. So this becomes the integral of dV. So often you'll hear compression work called PdV work. So here, the pressure is going to change. It's actually going to be a function of volume, so we need an expression for that. So if we assume that this material behaves as an ideal gas, we can use the ideal gas law that says PV is equal to mRT. And in fact, T is a constant, so I'll call it mRT naught. So that, for example, is equal to that constant C. So I can go ahead and replace the pressure as C over V. So now let's go ahead and calculate our work. The integral of the pressure is this constant over V dV. You can pull the constant out of the integral, which becomes C, natural log of V2 over V1. And this constant, I see, is equal to mRT, but it's also equal to the product of PV. So I can go ahead and put that in there and make this P1 V1 natural log of V2 over V1. And I'm choosing P1 and V1 instead of, for example, P2, V2, because I know it. They're actually already given in the problem. So if I put those numbers in there, I have 100 kilopascals for my initial pressure, my initial volume of a cubic meter, and the natural log of the final volume over the initial volume. And that number right there, if I look at the final value, is minus 69.3. My units are kilopascals meter cubed, so that's equal to a kilojoule. Let me mention something about this negative sign. Negative means that the system did negative work. In other words, work was done on the system, so its energy actually went up. All right, let's look at a couple more examples. This is one related to electrical work. And so we have kind of an Alaska example. We have a 250-watt block heater. So we plugged our car in on a cold night. It's going to go ahead and run overnight, about 12 hours and I want to know how much electrical work was done. Every time we do work problems, we can start with the same equation that says the work is equal to the integral of a force through a distance. We just need to now determine what's the force. In an electrical problem such as this, the force is the voltage. So I'm going to be multiplying the voltage by, well, the amount of distance it effectively goes is the number of coulombs it has, or dN. So N would be the number of coulombs. For electrical engineers, maybe anyone that's taken physics 212 knows that the amount of current that we have is equal to the number of coulombs per time. So in other words, I can go ahead and convert the number of coulombs that I'm doing to be equal to the current that I run times the time. So I can go ahead and put that in for the number of coulombs that I have. And so now I'm integrating the voltage times dN, which is going to end up being I, a constant current, dt. The voltage times the current is the power. So now what I'm doing is I'm integrating the power dt, and the power, if it's constant, in this case it is at 250 watts, this becomes simply the power times the time. So let's go ahead and calculate what that is. The work is the power, so we have 250 watts. The amount of time is 12 hours. And let's go ahead and convert this into seconds, because a watt is a joule per second, or a joule per second. So I have hours here, so 3,600 seconds is 1 hour. So now my hours will cancel, my seconds will cancel, and they'll end up in terms of joules. And this value right here equals 1.1 times 10 to the 7th joules. That's actually a pretty big number. And in fact, if we were to convert this into something, for example, say cheeseburgers, if we were to how many cheeseburgers would you need to eat to do this the same amount of work, we'd find out that that is almost 8 cheeseburgers. So it's a good thing that we can plug our cars in and we don't need to do our work ourselves. Okay, so let's do another example. And this is one that might be relevant for civil engineers, where I'm going to go ahead and stretch, for example, a 50 centimeter long bar with a 2 centimeter diameter, a distance of 1 millimeter. And I'm told what the Young's modulus is. It's 200 gigapascals. So if you think back to a class like es346, you probably saw stress strain curves where if you have an elastic material, that would be a straight line. You've got sigma versus epsilon, and the slope of this is the Young's modulus, sigma over epsilon. And this is the strain, or the change in length over its initial length. So if we look at our work equation, which is the integral of a force through a distance, this is equal to, well, the force is pressure times area. Pressure is the same as sigma. So this is going to be the equal of sigma area times ds. So ds is the length that I'm going. So if I look at my strain equation that I have here, I could go ahead and say that d epsilon is equal to dl over L naught. So in place of ds or dl, I'm going to put in L naught d epsilon. This is going to become sigma a, and then ds is going to be L naught d epsilon. So I'm going to do one more final substitution. For this sigma value here, I'm going to put in the Young's modulus as E times epsilon. So now my work is going to be the integral of E epsilon A L naught D epsilon, and we can go ahead and do that integral. Now, a lot of these are constant. E is constant, A and L naught is constant. So this ends up being equal to 1/2 E A L naught epsilon squared. So let's go ahead and evaluate that, put our numbers in here. So we're going to have 1/2, and E is 200 gigapascals, or 2 times 10 to the 11th pascals. My cross-sectional area, so if this is a circular cross-section bar, it would be pi r squared. So I'll do pi, and the radius would be 1 centimeter, or 0.01 meters squared. So that's the area, pi r squared. L naught initially is 1/2 of a meter, 0.15 meters. And now epsilon squared, how much is my strain? And my strain is going to be 1 millimeter, 0.001 millimeters over 0.5 millimeters. And I go ahead and square that. So go back and do our last number on here. If I calculate all of this out, I'm going to end up with a numeric value that's about 62.8 joules. It's actually a really small number. Last time we looked at our electric block heater, it was like 10 to the 11. Here we're only at about 62. So although doing the work is actually hard to do, you don't end up doing very much work at all. All right, let's talk about a couple more types of work. And here what we're actually going to do is see where those equations for kinetic energy and potential energy come from, this initial description that we have here. So recall for acceleration, the force is equal to mass times acceleration. And acceleration is, well, it's going to be the change in velocity with time. So if I was to go ahead and put that into that equation here, now I've got the force is equal to mass times dv dt. And velocity is ds dt. So therefore, I could say that ds is equal to v dt. So now let's go ahead and do our work for acceleration, which is equal to the integral of a force through a distance. So I'm going to go ahead and put in my m dv dt. And then I've got my ds, which is v dt. And my dt's cancel, and I find out that this is the integral of m v dv, or 1/2 mv squared, which we recognize as kinetic energy. We can do a similar thing for potential energy, where now the force is equal to the mass times gravity, where now the acceleration is constant. The acceleration is gravity. So this integral becomes a little simpler. My work is the integral of force through a distance, which is mg ds, an integral there. And if I'm going upwards, if I call that distance, for example, z, this would become the integral of mg dz, or simply mg delta z, which we recognize as potential energy. All right, let's go ahead and do one final example here. This is related to acceleration of a person. They weigh 80 kilograms. They're riding a bicycle at a velocity of 15 kilometers per hour. They encounter a 10-degree slope, and we want to know what additional power is required to remain going at 15 kilometers per hour. So you can imagine, here's my slope. That is 10 degrees. And I've got a bicycle there going 15 kilometers per hour. So what we're going to know is the additional power. So we might call that power is work per time, or I could just put a dot over it, think of it as work per time. So what I'm trying to find is the work per time. I'm going up, so this is a change in elevation. So work we just saw for increases in potential energy is mgz, and so work per time would be mg dz dt, where that is the rate at which we are moving upward at this 10-degree slope. Let's go ahead and put some numbers in there. Our mass is 80 kilograms. Gravity, about 9.8 meters per second squared. And now dz dt, how quickly are we going up? Well, we are moving at 15 kilometers per hour, and then we're going to multiply that by the sine of 10 degrees to tell us what percentage of this 15 kilometers per hour we're going up. And now let's go ahead and convert our 1 kilometer into 1,000 meters, and our 1 hour into 3,600 seconds. So our hours are cancel, kilometers cancel, and so what we're going to end up with now is going to be units of joules per second. And so if I go ahead and multiply this, I find out this is 567 joules per second, or 567 watts.